Hey everyone! This video is on how to go from a time domain graph of a signal to predicting what the frequency spectrum is going to look like. Most of these problems usually come across as matching time domain graphs to frequency domain graphs. I want to help you get the intuition and the general procedure for just looking at one of these time domain graphs and predicting what its frequency spectrum is going to look like. So we'll start here with x1 of n. Now, immediately I can see that this is an alternating signal, right? It's going back and forth. You cannot see that color very well. It is going back and forth across the x-axis. It's essentially symmetric across the x-axis. So I can probably say that the total sum of this signal for all time is going to be 0. That means I know that in the DTFT, or the frequency spectrum, the magnitude at 0, or at omega equals 0, is going to be 0. This means that I'm not going to have any peaks in my frequency spectrum at omega equals 0. Now the other thing I can realize here, and this is a mathematical observation I want you all to be able to make, is if you remember in pre-algebra when you were first working with sinusoids and different kinds of trigonometric functions, you learned about damped sinusoids. You can see here that this signal looks like a sinusoid that is damped, right? It's starting small and then it's getting bigger and it's getting bigger and it's getting bigger. And if you remember from pre-algebra, that happens when you have two sinusoids multiplied together. You get this characteristic oscillations increasing kind of image. So we know if we have two sinusoids multiplied together, think two cosines multiplied together, that's modulation. This graph is going to look like a modulated signal graph. Modulated. And we know that looks like, if this is 0, some peak, mirrored peaks on either side equidistant from 0 at whatever our modulated frequencies were. We don't know what those were, but we do know that the frequency spectrum plot of x1 of n should be 0 at omega equals 0, and it should have these two mirrored peaks because this is essentially a modulated signal. Great. Let's look at x2 of n. This one is really simple. Don't overthink it. This just looks like a part of a normal sinusoid. There's only one frequency in here. When we take the DTFT, what we're really doing is breaking up this time domain signal into all of its frequency components. There's only one frequency component in this signal. It's this relaxed sinusoid that we've just essentially truncated a little bit of. This means that our DTFT, or let me amend that, our spectrum magnitude plot is going to only have one frequency in it, because there's only one frequency in this graph. That just means we're going to have a plot that looks like this, and there's just one frequency somewhere. That's it, one spike. Great. Looking at our next x3 of n, what does this look like to you? This should remind you of a low-pass filter. Low-pass filters are essentially rectangular. They are 0 everywhere outside of some range, which means that this, in the frequency domain, is a sinc function. Something that looks like a low-pass filter or rectangular in the time domain looks like a sinc function in the frequency domain. Now this is a relatively short width rectangular pulse, which means in the frequency domain it's going to look like a wider sinc, and that's going to look something like, excuse my terrible drawings, but essentially something like that, because that's what a sinc function looks like in the frequency domain. If we look at x4 of n, this looks essentially the same as x3 of n, except it's wider. It's got this wider width. The rectangle is longer. It's going to look like a sinc function again in the frequency domain, but it's going to look like a narrower sinc. It's going to look like something like that. So the takeaway here is that a shorter rectangular pulse in the time domain corresponds to a wider sinc function in the frequency domain, and a wider rectangular pulse in the time domain corresponds to a narrower sinc function in the frequency domain. Now we move on, and x5 and x6 look like sinc functions. Now, we just said that a rectangular pulse / low pass filter in the time domain is a sinc in the frequency domain, and the converse holds as well. A sinc in the time domain is a rectangular shape in the frequency domain, except remember, we don't have perfect rectangles usually in frequency plots. They're just kind of sums of sinusoids, so they all look a little wavy. I'll explain this to you here. We have a narrower sinc here. This is a narrow sinc, which means it's going to be a wider rectangle. I'm going to put rectangle in quotation marks in the frequency domain. And what this will look like is 0, and then it goes up, and then it goes this little like wavy rectangle approximation, and it goes back down to 0. And here, all the waviness comes from the fact that this is some sum of sinusoids. Now, x6 of n is a wider sinc, which means it's going to correspond to a narrower pulse or rectangle in the frequency domain. That's going to look kind of like that, where this is wider and this is narrower. Now the last one is x7 of n, and there is a lot going on in this plot, and usually I don't want you to try to process of elimination match different plots to each other. If you've seen here, we've actually kind of predicted and made sketches of all the different plots we'll see for each of the time series graphs, but compared to everything else, x7 of n is really difficult to predict something for, right? Off the bat, there's not much we're really getting from here. It does look symmetric about the x-axis, so this is symmetric about x, so we can predict that the in the spectrum plot, the magnitude at omega equals 0 is probably around 0, and that there are a lot of frequencies. The more complicated your time domain plot looks, the more frequencies there probably are in the frequency domain plot. So I can honestly tell you that the magnitude plot of the frequency spectrum is complicated. I know that's not what you probably want to hear, but at this point, since you've identified everything else, you can take the frequency domain plot you probably don't have much of an explanation for, that looks really weird and crazy, and call it the frequency plot the magnitude of the frequency plot corresponding to x7 of n. And I'll attempt to draw what it actually looks like for you. It looks like we got these like two big peaks, and then it does go to 0 at 0, and then it has some other small bits of different frequencies, some big amplitude of some frequency, same on this side. And it's just really complicated. It has a lot going on. It has all of these little bits of different frequencies tailing off as well. So something that looks like you can't quite predict its frequency representation from the time domain, you're probably just going to match it with whatever the most complicated one is. Great. So I hope that was helpful. As always, if you have any questions, feel free to go to office hours or post on Piazza.